So I want us to look at some electrostatics concepts. I'm trying to clarify 4 different terms that sound very similar but are very different. And the first thing we'll do is define what electrostatics is. So in electrostatics, we are only observing properties and behaviors of stationary electric charges. So we're not going to look at charges moving through a circuit and forming a current. It's just the behavior and the particular characteristics of stationary charges. So the first thing that we'll look at is the electrostatic force. The reason we start with this is because it's something that we already have an intuition about. So we've been told for a long time that opposite charges attract and like charges repel. And in chemistry, we refer to this, I believe, as a dipole-dipole force. And it is basically at the basis of all of chemistry. That's why the compounds form. There is an electrostatic force between the positive charges and the negative charges. We call them nucleophiles and electrophiles. So nucleophiles seek positive charges and electrophiles seek negative charges. So those are the 2 different positive and negative charges, and it's something that we already know about. The magnitude of the electrostatic force is directly proportional to the magnitude of the 2 charges and inversely proportional to the distance between the charges squared. This is the electrostatic constant K. It's approximately 9 times 10 to the 9th. So this equation here will give us just the magnitude of the force. For the direction, we actually have to draw the diagram and draw the arrows for the forces that act between the charges. So here I have a positive and a negative charge. We know that they attract, meaning that the positive charge would want to move to the right, the negative charge would want to move to the left in this drawing. And these 2 forces have the same magnitude but opposite directions, and they act on the 2 different charges, so they are an action-reaction pair that we know from Newton's third law. For the 2 positive charges, I could have had 2 negative charges here as well. We know that the forces are repelling forces, so that means that this positive charge would want to go to the left. The positive charge on the right would want to go to the right. So we draw the direction of the force in that direction. Now, if we have more than 2 charges, then we have to draw the forces acting on the various combination of charges and then solve for the net force on a particular charge by doing vector math. So that gets a little bit more complicated. Now, how does a charge know that there is another charge in its vicinity, that it can be attracted or repelled by something else? Well, it knows that through the electric field. Let's look at an analogy. How does this bee over here know that there is a rose, a flower, in its proximity? Well, of course, there is a fragrance that this flower gives off, and the bee will just fly in a straight line, roughly, to get to the flower and collect the pollen. So you can think of the electric field as the fragrance. It's something that we can't see, but for the charge, the electric charge has the ability of making another charge come towards it or move away from it. So here we have a positive charge and a negative charge, and the electric field lines are radially outward from the positive charge and radially inward toward the negative charge. Essentially, these directions are given by how a positive test charge would behave if we placed it in the proximity of one of these charges. So if I put a positive charge here, knowing that these 2 will repel, the positive charge would move radially away from this charge, whereas the positive test charge over here would move toward the negative charge that's creating the electric field. So the electric field lines are given by the direction in which a positive test charge would move in the proximity of a positive or a negative charge. The magnitude of the electric field is directly proportional to the charge in magnitude and inversely proportional to the distance squared from the charge. And again, the proportionality constant is this K. Now, for these two concepts, you notice that we have magnitudes here, and we take the charge in absolute value. That's because a magnitude is a positive quantity, so we want both the electric field magnitude and the electrostatic force magnitude to be positive, and then the direction is going to be given by these arrows. So we always have to draw diagrams to figure out directions. Now, the third concept is that of the electric potential. So let's look at the rose and bee analogy. So you can think of this electric potential as the strength of the fragrance of the flower, and the ability of this flower to convince the bee to do work in order to come close to the flower and extract the pollen. So the electric potential then is similar to the strength of the fragrance, and we have to express that relative to somewhere else. So the strength of the rose is strongest here, and it's very weak very far away. So we have a relative strength of the fragrance, we have a relative electric potential. We'll go over that a little bit later again. Now, you have met electric potentials in chemistry, and you call them electrostatic potential maps. I stole this diagram and explanation from Wade's organic chemistry textbook. So what you have here is chloromethane, and this colorful image tells you which regions are more negative and which are more positive. So it tells you here that the red shows electron-rich regions, so this is more negative. Blue and purple show electron-poor regions, so this area is more positive. So essentially, the chlorine is more negative, and the 3 hydrogens and the carbon are more positive. So that's what the electric potential tells you, and what the electric potential map tells you in organic chemistry. Now in physics, we're looking at the positive charge with the electric field lines, and then the strength of these electric field lines, the ability, the potential of this charge to do work on another charge, to bring it in from somewhere farther away or to push it away from somewhere close here, is given by this electric potential. So the closer we are to the positive charge, the higher the potential, and then the farther away we go, the lower the potential. Same thing with the fragrance of that rose. The closer you were to the rose, the more fragrant it is, and then the farther away you go, the weaker it becomes. Now the equation for the electric potential is V is KQ over R, and you'll notice that we don't put these in absolute value at all, because we can have a positive potential or a negative potential, and the plus and minus signs don't stand for directions. So everywhere on this sphere, really, it's a three-dimensional thing, anywhere on this sphere, the potential is the same. Anywhere on that sphere, the potential is the same. So, there are an infinite number of potentials between the charge and that point, but I only drew 3 of them. The last concept is that of electric potential energy. So, the electric potential has the ability of doing work on another charge and bringing that charge in closer or moving it farther away. That's what I said earlier. So the electric potential energy is the energy between this charge and the other possible charge. So if I, for instance, brought 2 electrons close to one another, then held them in place there would be a lot of energy stored between them. They don't like to be this close together. So an analogy to that would be having 2 objects compressing a spring. Then there's going to be a lot of energy stored in this spring. We would have the spring potential energy in the spring, and we have the electric potential energy stored between these 2 charges. Now, if we let go of them, these 2 charges would shoot out in opposite directions and convert this potential energy into kinetic energy. Same thing with the potential energy in the spring. Once we let go of these two objects, these two masses, then they will shoot out, and the potential energy in the spring is going to be converted into kinetic energy in these two masses. The equation for electric potential energy is given by K, the constant, times the product between the two charges divided by the distance between the charges. And notice here again that we're not taking the charges in absolute value, so we can have positive potential energy or negative potential energy. And just like with gravitational potential energy, we have to express the energy relative to another energy. So with gravitational potential energy, when there was a difference in elevation between different points in the motion of a particle, we would say that the particle has a gravitational potential energy of mgh, where h is measured relative to a point where we chose the potential energy to be 0. Same kind of thing with the electric potential energy. Now we'll say that the relative electric potential energy would be the one where the two charges are infinitely far apart, because when r is infinity, then the electric potential energy is 0. So that would be a common relative electric potential energy. So now let's look at the math of these different equations, see how they are related, how we can go between them. So we start out with the electric field, which is due to each individual charge. So we say that in magnitude, the electric field is kq in absolute value divided by r squared. Now, if we multiply the electric field by another charge, we end up with the electrostatic force. So we have the electrostatic force is k q1 q2 over r squared. Again, this is just a magnitude. The direction would have to be drawn on a diagram. Now, I'm overly simplifying this and saying that if I multiply this electric field by a distance, then I would get the electric potential. So I'm saying that I'm oversimplifying it because the electric field is not a constant. The further away you go from the charge, the less the strength of the electric field becomes. So here we would really have to take an integral. But it's good enough for us at this point just to see the relationship between them. So the electric potential then is the electric field times the distance. Then if we multiply the potential by another charge, so we have V times Q2, we end up with the electric potential energy K Q1 Q2 over R. And remember from mechanics, when we first learned work, we said that work is force times displacement. And if I multiply this force by a distance, then I end up with electric potential energy. Work and electric potential energy have units of joules. So this is a relationship that we are a little bit familiar with already from mechanics. So these two concepts of electric field and electrostatic force, they are both vectors, so they have both magnitudes and direction. These other two concepts, electric potential and electric potential energy, are scalars. They can be positive or negative, but they don't have a direction. Also, these two quantities have to be expressed relative to a zero potential or a zero potential energy. So we have to use a delta V, a delta EPE, to express what these quantities are. Now, if I go backwards, so I went with my arrow to the right. Now, if I go with my arrow to the left, then I have the electric field being equal to the force divided by a test charge. So this gives me the electric field of charge Q1. If I go backwards from the electric field, from the potential to the electric field, then the electric field is the change in potential divided by delta X with a negative sign. And you can think of that when you're thinking of the electric field lines going away from positive and the electric field decreasing. If my delta V is from a farther distance from a charge minus a closer distance to the charge, then the negative sign brings the electric field back to a positive value. And then delta V is delta EPE divided by Q2. And last but not least, the force is the negative change in energy divided by R. And here we covered all of the different concepts. The units, of course, force is in newtons, which means that electric field is newtons per coulomb, but also electric field can be volts per meter. We know that energy is measured in joules. We divide joules by coulombs and get volts. So these are the different units and the different concepts.